Good afternoon, everyone. I would like to begin this presentation by going through the landscape of history a little bit. Everyone present here will agree that historically we have gone through what is called the Stone Age, the Bronze Age, and the Iron Age. One of the things that is common of these three ages remains materials. Stone Age happened to be when mankind didn't have the ability to transform the environment significantly, and therefore was only able to use what was immediately available, which is stones and every other thing associated with the natural environment, the rocks and stuff. And then at some point, it became important, and as history would have it, that the use of fire came into play, whereby mankind was able, after the development of fire, be able to take the natural things in the immediate environment to use fire to see what will happen to it. And that gave birth to what we call the Bronze Age, meaning material was able to transform from one state to another. And then with time, we went from mankind observing these responses of materials from the natural environment to heat, giving us different apparitions, which we call metals. So both the Stone Age, the Bronze Age, and the Iron Age are related to material science and engineering. The Stone Age, the material that was dominant is what we call today ceramic material. The Bronze Age and the Iron Ages would correspond to what we call today in materials field as metallic materials. And in the last 100 years, other types of materials known as polymers, as a result of our grand development in the world of science and engineering, evolved. And so the field of material science and engineering remains an amazing world and remains the definition of tomorrow. So where we are today is as a result of our ability to master materials and our ability to have the way of transforming materials beyond what was humanly possible in terms of sophistication. You can take the table in your rooms and you can reconcile that the tables could be made of wood coming from your trees, or could be made of metals, metallic materials, or could be made of anything. If you go to the natural parks, you are going to see the seats there made of cement materials and etc. So material defines our tomorrow. I would quickly refer us to the slide that we are viewing, where we have introduced the notion of structure, property, processing, and of course, performance. So these are the key things that define our field of material science and engineering. And on the left-hand side of this figure, you can see that deliberately we have used atoms to show us the fact that material science and engineering explores materials at different length scales, starting from what we can perceive at the atomic level to what we can perceive at the microscopic level. So material science, therefore, brings together the different disciplines of science, physics, chemistry, biology, and on. Now, 50 years ago, there was less of biology, but today we have biomaterials, bioengineering, and on. Therefore, our tomorrow is always going to be defined by what we're able to develop based on material. As an example, illustrating what we mean by materials, on the left-hand side, we have aluminum oxide powder, which looks very much like any other compound, like your salt or sugar. And on the right-hand side, you can see that there are three slabs, or rather three chunks of material that are displayed on the background of a text material. And on one of them, we can read through what is written at the background. On the second one, we can see a semblance of light going through. And the third one, the disc there, is completely opaque. Now, all of them have one thing in common, and that's the powdered material on the left-hand side. And what they have in common is the atoms that make up these materials are the same. But in the material science and engineering language and parlance, we have been able to process what you are seeing on the left-hand side to what you are seeing on the right-hand side. So processing is what we call what we do to materials to make them to become useful. Therefore, field of material science and engineering in the last 50 years, 20 years particularly, has seen tremendous advancement to the point that anyone from any field, physics, chemistry, and engineering, not necessarily from material science and engineering first degree, can naturally take up this field of study and blossom in his or her future aspirations. Taking this a little bit further, I like to use this particular illustration here to give us an impression of what we mean by material understanding at different length scales. On the far right-hand side, we have a quartz material, which most of us may know. By the way, quartz is a material that is used in making a radar and things of that nature. And what you see on the far left-hand side happen to be the atoms sequence arranged to giving us the material types we see on the right-hand side. So our silica was made of silicon and oxygen atoms arranged in a perfect way, gives us what we call a crystalline material. And then if for any reason we are able to alter this arrangement to give us the next pattern that we see on the left-hand side, we call that amorphous. So the difference between the two arrangements is one has regularity of arrangement of pattern, and the other one is completely random. These two arrangements, if we retain them in solid states, we have two different materials. So our glass material, as we naturally will call and identify crystals, is the amorphous type, even though today we have come to develop ways of making glass also to be crystalline. Now, if you look down on the third column, you would notice that the amorphous pattern can be made to aggregate into well-ordered pattern, and that will give you what we call the colloidal crystal. And on the fourth column, you see that the amorphous pattern can be made to aggregate and arrange into an irregular pattern. And so that gives you your colloidal glass. My good friends, these are different ways illustrating our ability to manipulate materials at the atomic levels, at the molecular levels, and at what we call nanometer level, spanning to what we call microscopic level, and therefore macroscopic level. Therefore, at the level of chemistry, a chemist may be focused on studying how these atoms are bonded together, while a material scientist and engineer is now interested in, after the bonding has taken place, whether in the gaseous state or liquid state, how can I transform these materials into the solid state with spatial arrangements that will give them unique properties? And that is why we keep saying material science and engineering in action is what defines our tomorrow. And by the way, before I conclude quickly, shortly, what we have shown in these illustrations are extended in different kinds of materials, metals, ceramic, polymers, and composites. So I would conclude here and then let the next person to take place. So it will be our pleasure to recruit you into our program because your vista and your knowledge of materials and what you can imagine would simply, be very, very impressive and give you a wide range of options. Thank you so much.